Welcome to the end of Chapter 1, Section 1.4, the passage from finite to infinite dimensional spaces. Super brief section, so we'll be done with this video in about a minute. You're familiar with finite sums, and after Calculus 2, you're familiar with infinite sums. Nothing goes wrong with a finite sum. You add that finite collection of numbers together. But with infinite sums, that is with series, divergence becomes an issue. Kind of the big picture here is we want to take infinite linear combinations. In so doing, we'll probably be residing in infinite dimensional vector spaces. And I'm totally paranoid about divergence as well. We should be. Finite sums, simply a sum. Take an infinite sum, it may converge, it may diverge, fail to converge, this being the case in a number of settings. If we deal with just plain old numbers, you dealt with this in Calculus 2 when you were introduced to series. We could try a similar thing where we're dealing with matrices. We could maybe even try a similar thing if we were dealing with groups and binary operations in a group. Finite, no problem for any of the three. Infinite, problems. You can have divergence when dealing with an infinite sum of numbers, that is a series. Similar things could happen with matrices, and it may not even be meaningful to apply a binary operation an infinite number of times. It isn't meaningful unless you can talk about limits. The sum of a series is a limit. It's the limit of the sequence of partial sums. So without a limit concept, we can't take infinite sums. And even when we can take infinite sums, you got to worry about divergence. So to discuss convergence or divergence of infinite sums, we need a way to discuss limits. Let's say we need a way to measure distances. We need a metric. Now there's some other ways to deal with this that don't require exactly a metric. At least we need a topology. There's a section of the book devoted to topology. But for our purposes, let's say we need a metric. We need a way to measure distances. It's rather shocking you can measure distances without a metric, but it's doable. You talk limits. And you think of limits as some concept of closeness. But you can talk closeness without a metric, it turns out. We're not going to go there, at least not for several chapters. For now, let's say we need a way to measure distances. We need a metric. We'll make the passage, quote unquote, to infinite dimensional normed spaces, basically by replacing the idea of a finite linear combination with an infinite linear combination, and by throwing out the bad stuff. Okay, if we've got a norm, then we can talk about the lengths of vectors. Well, I don't want vectors of infinite length, so they'll have to go. And very informal at this stage. It'll be plenty formal before we're done. And it turns out the way we'll deal with infinite dimensional normed linear spaces, the norm will produce a metric, the norm will induce a metric, it's said. We'll be able to simply exclude vectors of infinite length, and it turns out you'll be good to go. You can take your infinite linear combinations of these kinds of vectors. Now, that's quite a mouthful to show, and we'll have to go through some arguments about these things. But we'll start chapter 2 dealing with, I believe it starts with norms, so we'll deal with normed linear spaces in chapter 2, and the motivation there is I want to do infinite linear combinations. I want to do series in the linear combination setting. And to do so, we need a concept of limits. And for that, we need some type of metric. And the norm will give us a metric so that we can do limits, so that we can do infinite linear combinations. So that's the big picture and where we'll start in chapter 2. So I will see you there. Bye-bye.